All right, we're going to go ahead and get started. And I should have finished this yesterday. Tedder had me all messed up walking in, but it's okay. All right, some interesting conditional probability questions involving going in reverse on a tree diagram. Here's one related to the previous example. Suppose you're watching a recording of one of Federer's matches from 2011 and he's serving in the current game. You get distracted before seeing his first serve, but look up in time to see Federer win the point. How likely is it that he missed his first serve? So to find the probability, we're going backwards in this probability tree that we made. To find the probability, we start with the result of 1 point, which is displayed on the second set of branches in the above figure, and ask about the outcome of the serve, which is shown on the first set of branches. We can use the information from the tree diagram and the conditional probability to do the required calculation. So what is this? It's the probability that he missed the first, given that he won the point. Okay, so again, it said, how likely is it that he missed his first serve? So we know that he won. So given that he won, we want to know the probability that he missed, given that he won that first serve. So remember, our formula says the probability of miss and win over the probability of win. Back to the other page that we had, here's our chart. We already found this, the probability of miss and win. We multiplied these two together and we got 0.2109. So I want you to know where it came from. We've already done it. So if you flip back, you'll see it. Miss and win is 0.2109. And then at the bottom of the page, we did the probability of winning. So make and win, miss and win totaled together is 0.7023. So the probability of winning is 0.23, which gives you a percentage of 0.3003. So that's about a 30% chance that he missed his first serve. All right, we're going to keep doing these. So we're going to do another one in just a second. Okay. All right. Who visits YouTube, tree diagrams and conditional probability, video sharing site led by YouTube, should be sites, led by YouTube are popular destinations on the internet. Let's only look at adult internet users ages 18 and over. About 27% of adult internet users are 18 to 29, another 45% are 30 to 49, and the remaining 28% are 50 and over. The Pew Internet and American Life Project found that 70% of internet users aged 18 to 29 have visited video sharing sites, along with 51% of those ages 30 to 49, and 26 of those 50 or older. Do most internet users visit YouTube and similar sites? Suppose we select an adult internet user at random. Draw a tree diagram to represent the situation. So we'll start with that one. And then we're going to start with our age groups. So how many different age groups do we have?
Three.
So I'm going to make 3 branches. The first one was 18 to 29. The second one was 30 to 49. And the third one was 50 plus. Tell me about those 3 age groups, the percentages. Um, 27 was 18 to 29. 45 was 30 to 49. And 28 was 50 plus. All right, it says the Pew Internet and American Life Project found that 70% of internet users aged 18 to 29 have visited a video sharing site. So Some have either visited or not. And it's the same thing for all of them. So for 18 to 29, it says 70% have visited. So how many have not? Yeah. Zoomers, don't let Mary Kate answer every question, please. All right. 51% of those 30 to 49 have visited. So somebody on Zoom, how many have not?
49.
And then 26 of those are 50 or older. 26%. So that means how many have not visited? 74. That's it. That's your tree diagram. Okay. Part B says find the probability that this person has visited a video sharing site and show your work. So it doesn't say anything about ages. It just says anybody has visited. So you have to do all age categories. So how would I do that? You're going to add up not just the visit. What else do you have? The age groups. So anytime you're doing this and you go to visit, how can you get a visit? So make sure that you go all the way back through your chart. So for 18 to 29, there are 27% that do go on the internet and 70% of those visit a site. Does that make sense? Then we have 30 to 49, where 45 go on the internet and 51% visit those sites. Then we have 28% that are 50 plus, and 26% of those that visit a site. You put that all together, guys, you will be doing this on your test. And you get 0.4913. Interpret that for me. Just to keep it consistent with everything we did yesterday, your answer is correct, okay? There's a 49% chance of all adult internet users having visited a video sharing site. All right. So given that this person has visited a video sharing site, find the probability that he or she is ages 18 to 29. So how would I write that? The probability of given visit, yes. 18 to 29, given the visit. So what is our actual formula for that? What's going on top? Probability of in words. A and B, which is, yeah, you're fine. 18 to 29 and visit over the probability of what? Nope. It's always the second one. Always the second one. So probability of visit. All right, so we're going to look at our tree diagram really fast. Here's your 18 to 29, so 0.27, and your visit is 0.70. So we're going to put those two together. So this is going to be 0.27 times 0.70. And again, that's from your tree branches. And then what was the probability of having a visit? We just did it. 4913, which gives you a total of 0.3847. Make sure when you put this in your calculator, you either put parentheses around the top or you do it like that, alpha y equals, so it's actually a fraction. Otherwise, if you just type this in, it's going to divide 70 by 4. It'll be weird. So just be careful that it doesn't do that. Okay. So then interpret this. What do we say first? What was this? What's this line mean? Given that. A person does what? Visits a video sharing site. I just put VS site. There is a 38, and you can put the whole thing, 0.47%, or you could say approximately 38. You could say 38.4. It doesn't matter. 38.5. Chance what? Yep. Years old or age, 18 to 29 years. Very good. All right. I'm going to do it again. Is everybody good? I'm going to flip it. Tell me if you're not. All right. One of the most important applications of tree diagrams and conditional probability is in the area of drug and disease testing. So many women choose to have annual mammograms to screen for breast cancer after age 40. A mammogram isn't foolproof. Sometimes the test suggests that a woman has breast cancer when she really doesn't, which is a false positive. Other times the test says that a woman doesn't have breast cancer when she actually does, which is a false negative. Suppose that we know the following information about breast cancer and mammograms in a particular region. 1% of the women ages 40 or over in this region have breast cancer. For women who have breast cancer, the probability of a negative mammogram is 0.03. For women who don't have breast cancer, the probability of a positive mammogram is 0.06. A randomly selected woman ages 40 or over from this region tests positive for breast cancer in a mammogram. Find the probability that that she actually has breast cancer. Show your work. So look at your little bullet points. That tells you what your tree is going to look like. Okay, tells you what your tree is going to look like. So the very first one, 1% ages 40 or over. The age doesn't matter because all of them are going to be 40 or over if they're getting a mammogram. So forget that they even put the age in there. So 1% of women in this region have breast cancer. So what are the other ones?
0.99.
Of what? So 0.01 has cancer, right? What about the other ones? Do not have cancer. So that's your start. 0.01 have cancer. .99 do not have cancer. So I just put no cancer. But when they get a mammogram, they have a probability for women who have breast cancer. So we're looking at this one, have cancer. The probability of a negative mammogram is 0.03. So what are the two outcomes of the mammogram?
False positive or false negative?
We don't even worry about false. We're just going to go with positive and negative. Same thing on this one. These will tell you whether it's a false positive or not. So for women who have breast cancer, a negative, which is this one, is 0.03. So what would the positive be? 0.97. That's your second bullet. For women who don't have breast cancer, That's this one. The probability of a positive mammogram, that's that false positive, y'all got that? Is 0.06. So what would the negative be? There you go. All right, so there's your tree diagram. Now let's answer the question. The question says, a randomly selected woman ages 40 or over from this region. We know that she does test positive. This is given. She does test positive. We're trying to find the probability that she actually does have breast cancer. So what is the probability we're trying to find? Yep. It says, what's the probability she has cancer? So that's cancer. But we were given a positive. So just watch that. That given is what's going to mess you up sometimes. Okay, be careful. So on the top, cancer and positive. What's going to be on the bottom? Probability of positive. All right. So cancer and positive. So we're only looking at this one. What's your probability of cancer
0.01,
and probability of positive?
0.97.
You have to multiply those together, okay? So 0.01 and 0.97. Now the bottom says the probability of positive, all positive, not just positive cancer and not just positive no cancer, positive all. So how would I get a positive on the top? Same thing we did on the top. But we also could get a positive if we don't have cancer. So we have to add that probability in. So what is that one that we're going to multiply together? You just say them backwards. It's perfect. It's perfect. So the probability of no cancer causing a positive. We put this into our calculator. The top will give you 0.0097. The bottom will give you 0.0691. And it'll finish out with 14%. All right, so what happens? Let me tell you right now, please pay attention. This bottom part is what gets you every time. Okay, make sure that you do the total positive. A lot of people will just put the first one on there, they'll just put the second. Make sure that you add the total in there. Interpret it.
14% of women who are positive for, who test positive for breast cancer actually have breast cancer.
Say it one more time.
14% of women who get tested for breast cancer and test positive actually have breast cancer.
Okay, I would be okay with that answer. You just got to think about it a little bit. All right. So again, keeping it consistent. There is about a 14% chance I didn't say it on the last one. That a randomly selected woman has cancer. Why do we say that? Given that a woman has cancer, you can say that as well. There's a 14% chance. Given that her test was positive. Any way that you say this is fine. It's not gonna, like, there's no super specific way that you could say it. You could say, given that a woman tests positive for breast cancer, there's a 14% chance that her test was positive. Doesn't matter, okay? Whatever you can say to get it across. All right. Are you surprised by the final result of the example? Most people are. Sometimes a two-way table that includes counts is more convincing. To make calculations simple, we'll suppose that there are exactly 10,000 women ages 40 or over in the region, and that exactly 100 have breast cancer. That's 1% of the women. So that's what they just made easy numbers for you, okay? How many of those 100 would have a positive mammogram? So it's just showing you in a chart now instead of in that tree diagram. It would be 97% of 100, or 97 of them. That leaves 3 who would test negative. Again, so all it's doing is taking those percentages from this last page we did and putting in them actual numbers. That's it. So it's nothing new. How many of the 9,900 women who don't have breast cancer would get a positive mammogram? 6% of them, or 0.06 times 9,900, which is 594. The remaining, how do we get the remaining? We subtract them. 9,306 would test negative. In total, 97 plus 594. So 97 had the positive mammogram. These didn't have cancer. Sorry, y'all, they got a positive. I think I'm dying. Excuse me, equals 691. Sorry, it's not stopping. All right, so 691, it's making it eyes water, would have a positive mammogram. So summarized in the chart, if you had 10,000 people, so 10,000 women, 97 would actually have breast cancer with a positive mammogram result. $594 would not have cancer but have a positive mammogram result. That's where your total 691 comes from. Excuse me, y'all. If they have cancer with a negative, there's only going to be 3 of them. 9306 would not have cancer and would have a negative. So that would give you 9309, and then adding them up. 100 have cancer, or that 1% have cancer. 99% do not. So again, all that did was put that tree diagram into actual numbers instead of just having percentages. Given that a randomly selected woman has a positive mammogram, the two-way table shows that the conditional probability, the probability of cancer given a positive, is 97. So cancer and positive is 97 over your total positive was 691, gives you 14%. Okay, so again, it just does it with numbers. This example illustrates an important fact when considering proposals for widespread testing for serious diseases or illegal drug use. If the condition being tested is uncommon, in the population. Many positives will be false positives. The best remedy is to retest any individual who tests positive. All right, so just throwing it out there, last Thanksgiving, my sister had a negative, like a freaked out mammogram or whatever, so they made her go back and she tested fine. So a lot of times there is a false positive, but it's better to be on the safe side than not.
That happened to my mom.
It's crazy, isn't it?
Happened twice now.
It's crazy. All right, check your understanding. I'm gonna try to get through this without dying. A computer company makes desktop and laptop computers at factories in 3 states, California, Texas, and New York. The California factory produces 40% of the company's computers, Texas 25%, and New York the remaining 35%. Of the computers made in California, 75% are laptops. Of those made in Texas and New York, 70 and 50% respectively are laptops. All computers are first shipped to a distribution center in Missouri before being sent out to stores. Suppose we select a computer at random from the distribution center. Construct a tree diagram. So what's my first branches of my tree? What do the first percentages tell you?
The different states.
Uh-huh. So what are your different states?
California, Texas, New York.
Perfect. What are your percentages for California, New York, and Texas, or Texas and New York? California was
40,
40. Texas was,
35,
and New York was
35.
35. What do they do? What kind? Or
Desktop.
laptops or desktops? Okay. Of the computers made in California, 75 are laptops. So California, 75 are laptops. That means how many are desktops? 25. Of those made in Texas and New York, so start with Texas, 70 and 50% respectively. So Texas had how many laptops? 70. And New York had 50. So in Texas, how many desktops? And in New York? 50. If I run out of time, we'll come back in, okay? That's your tree diagram. You're done with that. 2, find the probability that the computer is a laptop. So the probability that it's a laptop. How many different probabilities are we going to have for a laptop? 3, because we have laptops from California, Texas, and New York, right? All right, so how do I get the one from California?
0.75 times 0.40.
Good, or the other way around, it doesn't matter. Plus, we have to do Texas. Texas is? And again, doesn't matter which order you put it in. And then we have New York. And I'm going to go ahead and tell you when you multiply those together, you get 0.65 or 65%. It doesn't ask you to interpret. I've been interpreting it just so when it happens, you guys don't know how to do it. Given that the laptop is selected, what is the probability that it was made in California? So what's our probability? You do need to know how to write these out. So you have to write them. Okay, so what's my formula? On the top, what am I going to have? On the bottom? And we already did that percentage just right here. So we got to find California and laptop. So we got to go back to our tree diagram and just look at California. California and laptop is what? How do I get it? And then we did, the probability of a laptop was what? Mhm. And I'll go ahead and tell you that that is 0.462. That's it. If you guys know how to do that, you're gonna be in good shape. All right, I'm gonna go ahead and go out and come back in for this last part. And I do want to finish it. Sorry, guys. Stop share, stop.